All right. I would encourage you to read chapter 7. Look right here before we go too far. Like, I got an email from someone in this room, and I love you still, the morning of the test, before you took it, asking about when the retake is going to happen. What is wrong with you people? Prepare the first time. It wasn't. Like, if you just study and keep up, my tests are not awful. I usually will go over the test. I'll usually show you questions. I usually will, while I'm teaching it, say, this is on the test, yada, yada, yada.
Oh, yeah,
But
the last test, I got pictures of the test and took the board and it also
weird.
When you cheat.
It actually wasn't the same test as
Yeah.
Yeah.
All the numbers were different, so it was fine.
I didn't take the picture.
Okay, here we go. Chapter 7 is a why chapter. This is important.
Why chapter?
It's why. Like, it's not just I know that the bigger atoms are in the bottom left. Like, you need to know that, but you need to know why. The why is the 3 points. The trend is 2. So each one of these questions will be worth 5. 2 points to identify the trend correctly, 3 points to tell me why. All right, so why that trend exists. No, I mark it all wrong. All right, so not only is it important to know the periodic trends on the periodic table, it is also important to know why the trends are the way they are. In the vocabulary list, you can find that on Canvas if you want. Make sure to include the reasonings for the trends. This is a memory chapter, so a good set of descriptive flashcards may help. That's up to you. All right, here are the trends that you will be held accountable for. I did this real quick right before lunch. There may be more, but I'm pretty sure this is it. So you need to know the trend for effective, I think it's effective, whatever, it doesn't matter, nuclear charge, atomic radius of atoms and ions, atomic radius of ions versus parent atoms, ionization energy, and electron affinity. Those are the trends that you are held accountable for. You're doing great. Thank you. Yep. All right. Then, if you want to test retake, you can have one. This is what you have to do, though. You can only take the retake after you've done the Chapter 7 blue sheet and turned it in, and after you've watched all the Chapter 7 videos on Edpuzzle. There's 2 of them I assigned today. You don't have to do them. Like, I'm not going to grade them. But if you want to retake the test, there's going to be more than that. There'll probably be 5 Edpuzzle videos.
So it'd be beneficial to know now.
It's up to you. You're not going to have to retake a test probably. You don't. Like, you have taken one, but you didn't need to. You just did it because you wanted a better grade, even though you already had a great grade. But this is to help you learn and also be discouraged from just planning to fail and then retake over and over and over. Because this will probably take 2+ hours on those. Okay, so I'm not trying to be a jerk. I'm trying to make you work harder the first time, which is good for you. Just so you know, there are no retakes allowed in college. Never, ever, ever, ever. I don't know why we do it to you in this high school. It makes you like dependent on retakes, and then you go somewhere where there aren't and you struggle. I think we do everyone a disservice. Now, you maintain your 4.0s, but I think most of you would still have a 4.0 even if we didn't have retakes. Okay, fair enough. I'm going to move on. So this is the first section of Chapter 7. I'm spending 30 seconds on it. The periodic table looks like this. It is arranged this way based on chemical properties and physical properties. This chapter has a lot to do with physical properties. All right, elements in the same group, that'd be the same vertical column, have similar properties. They're not exactly the same, but they're similar. Okay, It's like my family were the Davidsons. We're all Davidsons, but we're all a little bit different. Yeah,
So like family one are similar, but they're different.
they're all really similar, but they have different property, like slightly different properties. Okay. Next, Dmitry Mendeleev and Lothar Meyer they independently came to the same conclusion about how elements should be grouped. And you don't need to worry about this, but just know it happened around 1863. There were elements that were not even discovered yet, and it was pretty cool. They figured, hey, we don't know these, let's just leave them blank because we'll eventually find them. And all they've done is continue to find things that they didn't know before. It's pretty cool. Okay, whatever. This is just a story you can read. So, how he left openings because he knew things had to be there. All right, in this chapter, we will rationalize, observe trends in sizes of atoms and ions, ionization energy, and electron affinity. So, a typical test question, let me find one real fast. I'll come back, don't stress. I just want to show you like what the test will look like. Oh man, I thought there would be more at the start. Well, geez Louise, Tom, maybe they're all the way at the end. There we go. I could have sworn they were closer. So it says use details from the atomic theory, periodicity, or electron configuration to explain why. So as we go through this chapter, think about how to answer these type of questions. Atomic radii become larger as the atomic number within a group gets larger. This is already telling you the fact, so you don't need to worry about it. And like a wrong answer would be because they get bigger. It's like, I know that, but why? Okay, so you'd have to explain. They become larger as you go down because you're adding more principal energy levels and electron repulsion. So you'll learn why, but that's the style of question you're going to be asked. So think about that as we talk about these trends, be able to answer why. Okay, so just diving right in. And we talked about this a tiny bit in the last chapter when we talked about photoelectron spectroscopy. We talked about the attraction of an electron to its nucleus. Does that sound familiar? We called it the nuclear charge. All right. It's another name for it is the, what was it? The effective nuclear charge. It's the same idea. It's the attractive force between the nucleus and the outermost electrons. And it's any electron, but we mostly worry about the valence electrons. All right, so in a mini electron atom, electrons are both attracted to the nucleus and repelled by other electrons. The nuclear charge that an electron experiences depends on both factors. So that's what this beautiful picture is right here. You have this electron right here, and we're trying to figure out the force at which it's attracted towards that nucleus. And it's a balance between two things: how hard it's being pulled towards the nucleus because the opposite charges, and then how much it's being pushed away by other electrons. All right? So this effective nuclear charge based on two things: attraction to the nucleus and repulsion from other electrons. Okay, now, effective nuclear charge is sort of a pain in the butt to write. So it is abbreviated typically as ZEFF. So ZEFF for short. And we'll do a little tiny piece of math to learn what ZEFF is. Okay. Anyone need more time on this slide? ZEFF is how we determine an actual value for the effective nuclear charge. And it's not a real value, it's just a value we make up for comparison's sakes. All right, ooh, there's a lot of stuff here. I'll bring that back in a minute. So the effective nuclear charge, or ZEFF, is found in this way. ZEFF is equal to Z minus S. Z is the atomic number, and S is the screening constant, usually close to the number of inner electrons. And we will pretty much ride that train, that it is the number of inner electrons. So it's pretty simple. It's protons minus core electrons. Protons minus core electrons. That will tell you your Zeph. All right, so if I look at sodium, it's Na. It is element number 11. That's the number of protons. So to know the number of core electrons, I look at the previous noble gas on the periodic table. So I look left and there's nothing there. So really I look far right. And what's the previous noble gas to sodium? It's neon. And so how many electrons does neon have? Or protons, either one. It's 10, right? So 11 minus 10 equals 1. So sodium's effective nuclear charge is 1. Yes.
So will everyone in family 1 always come out to 1?
You bet it will. And any guesses what everything in family 2 will be? 2. You guys are smart. Well, you won't really do the math because you can just figure it out. But we need to know it so we can compare them. So magnesium, 12 protons. The core electrons or the screening electrons, it's the same. It's the previous noble gas. So we would say 2. Now, when we say a 1 and a 2, like I said a minute ago, it's just a comparison. Like there's no unit on that. It's not 1 Newton and 2 newtons, which you haven't had physics yet, but that's the unit of force. It's just the fact that we would say magnesium has twice as much effective nuclear charge than sodium. And if I did aluminum, it'd be 13 minus 10. It'd be 3. So aluminum would have 3 times the effective nuclear charge than sodium. Go ahead.
Noble gases, would you just do the one before? Or would
Yep, so there'll be 8.
okay.
Okay. So Zeph for a representative element is just equal to its family number. Go ahead, Cal.
Why are we always subtracting 10 from that?
Well, these we always did 10 because these were all on the 3rd row. And so their previous noble gas was the end of the 2nd row, which was neon. But it would be like if I wanted to do calcium, I'd take 20 and subtract argon, which is 18. Does that make sense? Okay. Core electrons are called shielding electrons. Now, the reason we care about this is when we start talking about a trend. So when I talk about the size, and we'll come back to this in a minute, but of an atom, size is measured by the distance from the nucleus to the outermost electron. So I would just take my little ruler and I would measure, all right, how far away is that? Well, think about what determines that. The thing that decides how far this electron is away is how hard the nucleus pulls on it, right? So if this was Na, what would you think magnesium would look like?
A little bit bigger.
You got it backwards. It'd be smaller. Why smaller? Tell your partner why it should be smaller. All right. Because I hear you all saying it. What's that? Okay, don't put that on your test.
But like I feel like everything always comes back to kissing.
Yeah. Aluminum is smaller because it has a greater effective nuclear charge. Okay?
So it literally is smaller. Like it
Yeah.
actually is a smaller, yeah.
Now, we got to be really, really careful. Make sure you listen to this part. When I say smaller, I mean like how big its three-dimensional sphere it occupies. I do not mean the mass. You okay with that? Like, because you would look at my son Derek and you'd say he's bigger than his dad, because he is. He's 4 inches taller than I am, but I outweigh him by 40 pounds. But you would look and say he's bigger, right? We, in our world, we base size on height usually. In chemistry, we determine it by the distance from the center to the outermost electron. Mass is, we don't talk about size and mass. That's just dependent on the number of protons and neutrons. Okay. All right. So aluminum, literally the atom of aluminum is much smaller than the atom of Na because we have a greater Zeph. If you will just think about Zeph as the number of rubber bands pulling something towards something, that'll make sense. If I have one rubber band between two sticks, it's going to pull about that hard. If I add a second one, and we're saying the sticks can move, by the way, all right, then it's going to be closer. If I have 3 rubber bands, it's going to be even tighter. That's, I've always looked at Zeph as just the number of rubber bands holding something together. You get it wrong. You need to put science words. All right, so.
It's like xenon a lot more compact than hydrogen, or
Well, that's tricky. Hydrogen is the smallest atom by far. And it doesn't seem to follow, it's all the way on the left. But hydrogen, so we know hydrogen's here and helium's here, but it can also live right here. Hydrogen is the smallest atom because all it has is one proton and all it has is one electron. And they live really small, or really close together. Helium is still really, really small, but it has 2 electrons, 2 protons, yeah, and they push each other just a tiny bit more away.
if it can be right there, does it behave like a halogen sometimes?
Yeah, absolutely, it can act like a halogen. Hydrogen can gain or it can lose an electron, so it fits in both.
So with like, would the thing with the biggest nuclear charge be like ATM? Or like, what would be the thing with the biggest nuclear charge? Or is it like every one that's in the seventh family?
Yeah, the nuclear charge is everything in the 7th and 8th family. Those are the biggest.
Okay.
But there's
So
there's up and down.
also radius or whatever.
Yeah, we'll talk about up and down because that's a good question too. All right. So, summary so far. I did this a year or 2 ago. Any of these blue things, they're a summary. Zeph, and they're going to build on each other. It's going to be the same thing repeating. It just gets longer and longer. Zeph is the attractive force between the nucleus and the outermost electrons in an atom. That's the definition of the effective nuclear charge, and you need to know that. All right. Zeph increases from left to right on the periodic table because we are adding protons, but the number of shielding or core electrons stays the same. So you'll read in your textbook, I hope, that your core electrons, they kind of shield the valence electrons away from the nucleus. Go ahead. In any of the chemistry books, it's chapter 7, unless your new version has completely different chapters. All right. All right, so we have what we call core electrons and valence electrons. Core electrons shield the nucleus, the valence electrons do not. Okay. So make sure you could explain or you could describe the trend and explain why. I don't know why there's an F right here. Well, it's T and then R, and then my E was too loopy. Oh. Okay, well, tell your partner real quick, Li or F, which one do you think would be the smaller atom? F is correct. If we were to illustrate, we'd put F about that big and Li about that big. All right. Next. All right. Okay, the book doesn't talk a ton about the up and down, but we need to know that as well. I thought it did. Let me see here. Just trust me for a minute. Okay, well, I'll just go to this slide. All right, so if I were to draw, and whenever I draw this, I always skip H and HE, just get over it. I'm going to draw relative sizes of atoms. And it will kind of give us an idea that size increases as I go down, and size increases as I come from the right to the left. So the bottom are big, the top are small, the left are big, the right are small.
What's the biggest?
Rubidium is typically described as the biggest atom.
Oh, really?
What's that? All right, probably cesium, not francium. Sorry, cesium is, but we don't measure francium because it's radioactive and falls apart. So I just had those backwards in my head. All right. Now, so the reason then we need to know is the why. That wasn't very well stated, but whatever. So we know left to right, why big on the left, small on the right. But now up and down, if I were to draw, I'd put one like right here. The reason why we get bigger as we go down has to do with chapter 6. And do you remember we did these boxes? Well, we were all having fun online. What's that?
Never mind.
Okay.
I hated this one.
What? Whoa.
It was the same thing we did in birth class. Yeah, I know, but
That doesn't mean she likes it. All right, here we go. It's okay, don't fight. We can all just get along. We were gone apart so long, and now we're going to come together and fight. That makes me sad. Okay, if you remember the 1s represented these, right? And we had the shape, we said it was just a small circle, but then we moved up to this and it was a larger circle. And then we moved to these and it was these. Does that sound familiar? Okay, and then this one, it was these, but like bigger than the one before. Sound familiar, all that? Okay, is on this diagram, as we are going up, we're actually going down on the periodic table. All right, so as we go down on the periodic table, we are increasing the number of shells. And the more shells, the more space the atom takes up. So when we got down here to cesium, I won't write the whole thing because it'd be a pain in the butt, but I would have xenon, which would have had a ton of stuff to write, right? Before we got to 7s2 or 7s1. I don't know why I put it 2. All right. All that stuff is places where there are electrons. Electrons occupy space and push each other apart. The more levels I have, the larger the atom. All right. Now, there's another subtle part right here. So there's 2 answers to this. Why it gets bigger as you go down lower. One is the addition of energy levels. And that's the most important of the two. And then the other answer, which you can put on a lot of these, is more electron repulsion. Whoops. A negative electron will push another negative electron away. They need more space.
So if it increases as electrons increasing, why isn't like the far right corner the bigger atom?
Because as I move from here to here, I increase the total number of positive things. That's my effective nuclear charge. So I have the same rubber bands essentially, like I keep adding one as I move over. But as I go down, the number of rubber bands stays one the whole time. But now I'm adding more electrons to push each other away. And the electron repulsion is what makes them bigger. The rubber bands is what makes them smaller. So the overall real answer to say is the addition of protons overcomes the addition of electrons by a lot, honestly. They'll pull way harder than the two push away from each other.
So would that mean like lithium and like xenon would be close in size?
I mean, they'd be closer in size, but whenever you try and nail me down on something real specific, I'm never going to do it. But we can look at this chart. We have a chart of sizes. All right, so lithium is 1.34, and you said xenon? 1.3.
Bro, look at me go. I'm so good.
All right, now, by the way, if you look at this, do you see some things are different than they should be?
The exception.
There's always exceptions. I am teaching you a general trend, but there are exceptions, okay? And we'll learn why. They're not that hard to explain. Okay, are we okay with this so far? So as of right now, we should understand Zeph. Uh-oh, I switched screens. And technically, the EFF is lowercase, but whatever. We should know Zeph, and we should know size, and we should know Y. We should be able to accurately describe.
What do you mean by lowercase?
Subscript is what I really mean, sorry. Z is really just, it's protons.
What does
No, it's protons.
The effective nuclear charge. It's like not mathematically exactly right. It's just one we're going to use to compare.
So it's protons plus core electrons.
Protons minus core electrons. Okay, let's come right here. All right, so we already talked about this, but here we go. The size of atoms is measured by what we call the atomic radius. The bonding atomic radius is defined as 1/2 of the distance between covalently bonded nuclei. You don't have to know that definition, but that's technically how they do it. They put two together and measure the halfway point. And so since that's half from the center out, we call it a radius or radii. We okay with that?
Wait, is that so why is that why they can't measure
Francium?
Yeah, because they can't put them together.
Well, you can put francium with stuff, technically, like you could, but the nucleus itself is just constantly decaying through radioactive decay. So if the whole atom's falling apart, we don't really measure it. All right. So you don't like really have to know the exact definition, but just know that's what we mean, the distance from the center to the outermost electron. Okay, and this is exactly what we were just saying. Bonding atomic radius tends to decrease from left to right across a row due to increasing effective nuclear charge. It increases from top to bottom of a column due to increasing the value of N. Now, the value of N, what is N? It's the rows, or it's called the principal energy level number. So, due to increased value of N or increasing number of principal energy levels. You can also add, there's greater electron-electron repulsion. So this is what I would do if I were you, because I know how my test goes and it would be useful. Start in your notes drawing periodic tables, just rough sketches, put arrows with an A and a B, label what it's talking about, and then explain A and explain B. Then you can use that as a quick study guide before you take the test. Yeah, you can take a picture. I don't care. I'm just saying this, a chart, to me at least, a periodic table that I've drawn and labeled and then explained below it in my notes would help me learn really well. When you read, I'm sure, you'll see a general chart like this. I have one, I'm pretty sure. Maybe. Melting point. Oh, I don't. Okay, I don't. I thought I had a 3D printed one of size, but they're of other things, and we'll talk about those later.
It'd be cool if you could make a 3D. I thought you 3D printed one across the wall.
That'd be a really big 3D printer. I might have one somewhere. Should be there, but it's not. Okay, well, anyway, so if you would memorize for size, the lower and lefter is bigger. It is now, my friend.
Yeah, they make new words every day. So.
Lower and lefter is bigger. Yeah, there you go. Lefties appreciate it. Okay.
It's kind of like how I left it.
Yeah, I left her hanging. That's mean.
I think Cooper comes up with more amazing sentences every time I've been here.
That was good, Lefter.
All right.
Oh, I have a lot. I got so basically all metals are straight.
Well, here's the answer. Here's something you'll see on the test. Non-metals are generally smaller than metals. Why? Tell your partner. I'm going to end the recording here so I can. Whoops. What do I want to do? That's what I want to do.